Okay, I want to devote this whole lecture towards the limitations of the crystal field theory. And like any other theory, even this theory has its own drawbacks, which we will be discussing in this present lecture. Okay, so starting with the very first limitation, you can see here is that the CFT or the crystal field theory considers the splitting only in case of the d orbitals and not in other orbitals of the metal, such as the s and the p orbitals, right? So here you can see that this is the electronic configuration of the cobalt, in which there are present these s orbitals here, which are the 1s, 2s, 3s and 4s. After that comes the p orbitals, which are the 2p and 3p here in case of cobalt, and finally the d orbitals, which are the 3d type of d orbitals here, right? And now the crystal field theory says that in the presence of an octahedral field of ligands, the splitting takes place in this way, such that the T2G orbitals comes down the barycenter line and the EG set of orbitals goes above the barycenter line, in which this difference here is what? It is the delta O, or the octahedral splitting magnitude in this case, right? So why it is only considering the splitting in case of these d orbitals only and not in case of these p orbitals or the s orbitals? So crystal field theory has no answers for this thing. Okay, so surely it is a limitation of this theory, right? So now coming on to the second important limitation, it does not explain the relative strength of the ligands in case of the spectrochemical series, which you can see here on your screen. On the left hand side are present the weak field ligands, which causes small degree of splitting, right? And on the other hand, on the right hand side, there are present the strong field ligands, which causes a large degree of splitting when the ligands approach the central metal ion. Okay, so now if we consider the case of the hydroxide and the water as ligands, what we will see here is that in case of the hydroxide ion as the ligand, let us say this is our central metal ion having a positive charge, and on this side is present this hydroxide ion, which is actually a negatively charged ligand, right? And surely whatever ionic bond will now be present in between this positively charged metal ion and this negatively charged ligand, it will be a type of an ion-ion interactions, right? On the other hand, if we are considering the ionic bond in between the metal ion and the water as a ligand, which is actually a neutral molecule, so definitely the ionic bond will be there in between the positive charge of the metal and this partial negative charge of this dipole here, which are present in the neutral molecules. So finally we can say here that the interactions in this case, I mean in case of water, are of what type? These are the ion dipole type of interactions. Once again, as far as the hydroxide ion is concerned as a ligand, the interactions are of ion-ion type. On the other hand, in case of water as a ligand, the interactions are what? These are the ion dipole type, right? And now moreover, I want to add here that the metal also contain electrons in its various orbitals, which means that it also possesses a negative charge. So when these ligands will be approaching the metal ion for the formation of such type of ionic bonds, there will definitely be present some sort of repulsions in between these negative charges, right? And now and this negatively charged ligand here, because a formal negative charge is present and it is higher in magnitude as compared to this oxygen partial negative charge, which is there in this case. And let me write here, this also contains its electrons, so a negative charge is also present here, and thus the repulsions will also be there in this case when water is present as the ligand, right? So now when both these ligands will be approaching the central metal ion, so in this case here where the ligand is hydroxide, because of the presence of a strong negative charge or a high magnitude of charge, according to this law here, what will happen? As the charge is higher as compared to this partial negative charge, so in this case what will happen is higher Q2 means higher forces here, higher repulsions, as well as the magnitude of splitting will also be higher as compared to this case, in which the charge is just a partial negative charge and it is not a formal charge. So definitely in case of water as a ligand, the quantity or the magnitude of this charge is quite low here, right? So this means the Q2 is low here, and thus the force which is directly proportional to the product of Q1 and Q2, this will also be less here, and thus the repulsions, let me write here, the repulsions arising will also be less here, and thus the splitting will be less here, less splitting will be there, right? So that finally I can write here that if we are comparing the hydroxide ion and water, in case of hydroxide, because it contains a higher charge, the magnitude of splitting should be following this order here, in which water will come on this side of this arrow and hydroxide ion will come on this side. Okay? But now I want to draw your attention towards our actual spectrochemical series, which you can see here. In this case, this order is completely reversed and it is towards water. This means that water is acting as a relatively strong field ligand here, because it is towards the side of the strong field ligands. On the other hand, the hydroxide ion is actually acting as a relatively weak field type of ligand, because it is present towards the weak field ligands category, right? So let me write here, this is actually acting as a weak field type of ligand as compared to that of water. But if we go according to the crystal field theory assumptions, the arrow or the sign should be like this here, means the amount of splitting should be higher in case of hydroxide as compared to that of water. Okay, but experimentally talking, it is just reverse of this thing. So we can say here that the crystal field theory does not explain this, this relative strength of the ligands here in case of the spectrochemical series. Okay, so this is the second important drawback of the crystal field theory, right? And now comes the pi bonding in case of transition metal complexes, and we will see here that the crystal field theory does not explain the formation of pi bonding in case of the transition metal complexes. Okay, now what the crystal field theory says is that it assumes that bonding is purely ionic in nature, such that the metal is having a positive charge, the ligands are having a negative charge, and there is present purely electrostatic type of interactions. Okay, so if you just imagine some metal complex here in which there is present a double bond in between the metal and the ligand. So what is this double bond made up of actually? This is a type of a multiple bond here, which is made up of sigma and pi bond, of course, and the formation of this bond can never be explained on the basis of crystal field theory, which assumes the bonding to be purely ionic, right? So is there any way by which this type of bonding can be explained? So I want to say here that yes, there is present another theory which can explain this type of multiple bonding in transition metal complexes, and it can be explained in this way here by this picture, in which you can see here that our metal is present here on this side and the ligand is present, the carbon monoxide is present on this side here, right? So now what you can see here is that when the ligand is donating electrons from its filled bonding molecular orbitals, it will result in the formation of a sigma bond, because the electrons are going towards the vacant metal orbitals. So the bond direction, and I can show here, is in this way. This means that the ligand is giving electrons to the metal ion. So I will be showing the direction of the bond in this way here, and will be resulting in the formation of a sigma bond here. So let me write here in this bracket, it will be a type of a sigma bond. It will be a coordinate covalent bond, because both the electrons are coming from the ligand itself, right? And now if the chemistry of this ligand here is allowing, what can happen here is that from the filled metal d orbitals, the electrons, which you can see here, these two electrons are present in the filled metal d orbitals, they can go back in this way, in this way or in this way to the empty antibonding molecular orbitals of the ligands, resulting in the formation of such kind of pi bonds here. So I will be writing here in the bracket, and I will write here a pi bond will be formed here, right? So 1 sigma and 1 pi will result in the formation of a double bond, something like this here. And the theory which explain this type of multiple bonding in case of metal and ligand is what it is, the molecular orbital theory, right? So this type of things can never be explained on the basis of the crystal field theory. So once again, let me read for you people that it does not explain the formation of a pi bonding in case of transition metal complexes. So another limitation of the crystal field theory. And moreover, it does not explain the presence of the charge transfer bands in case of the absorption spectra. So let me take example here, that is of the iridium 6 bromo 2 negative transition metal complex. And in this case, the iridium is present in the D5 configuration. If you go for the electronic configuration, it will come out to be 5 electrons present in the 5d orbitals, right? And the iridium actually belongs to the third transition series, right? So here on this side, you can see the absorption spectrum of this iridium 6 bromo 2 negative. And in this case, this axis actually corresponds to the molar absorbance. This one here is the frequency, and this one is the wavelength in terms of the nanometer, right? If you have a look on this spectrum here, it consists of two bands, two absorption bands. The first one is showing an intense absorption at 270 nanometers, and the second one is showing an intense absorption as 600 nanometers, right? Now, such type of bands are known as the charge transfer bands. This thing is actually different from those bands which arises because of the DD transitions, right? And we have various types of techniques by which we can differentiate these type of charge transfer bands from that of those bands which arises because of DD transitions. So right now, I'm not talking about the regular bands which arises because of DD transitions. We are talking only about the charge transfer bands and the various ways by which we can recognize that these bands are charge transfer bands. They are available, but let us not go to that side. Let us not deviate from our main topic here. So just remember that the charge transfer bands are something different from the regular type of bands. Okay. So in this case, I just want to say that if the charge transfer bands are arising in case of the absorption spectra, their presence can never be explained on the basis of the crystal field theory, right? So by what theory then this type of charge transfer bands can be explained? It is actually the molecular orbital theory, and it goes like this, right? So here you can see that the iridium d orbitals are present in the degenerate state in which all the 5 orbitals are having the same energy. Here is the barycentral line, and this will be the splitting in this case because it is an octahedral field of ligand. So 3 orbitals will come down here, down the barycentral line, and it will be the T2G set of orbitals, and 2 will go up here. This will be the EG set of orbitals, right? And here you can count the total number of electrons present in these degenerate d orbitals are how many? These are 5 in number because it is a D5 configuration for such kind of complex, right? And if you remember that while discussing the factors which determines the magnitude of crystal field splitting in case of transition metal complexes, I have told you that there is present an important factor, that is the type of d orbitals upon which the magnitude also depends. And it says that as we go from the first to the second and then from second to the third transition series, the size of the d orbitals goes on increasing, and thus the magnitude of splitting also increases, right? So now the iridium actually belongs to the third transition series. This means whatever d orbitals it has, they are of very large size, and as such in this case the magnitude of crystal field splitting will also be very high, which you can see here, right? So we can now show the preferential filling of these 5 electrons, and it will be like 1, 2, 3, and then 4 and 5 here, right? The 4th and the 5th electrons will not be going up here. The reason being this large or high amount of crystal field splitting, and it is greater than the pairing energy in this case. Okay, so it will be resulting in the formation of a low spin complex. Let me write here, it is what it is, actually a low spin type of complex here. But what we are interested here is that how the charge transfer bands are coming in this absorption spectrum, which are different from the regular type of absorption bands arising from DD type of transitions. And we are saying here that the presence of such kind of bands cannot be explained on the basis of crystal field theory. And here we are taking the help of the molecular orbital theory. Let us say on this side we are having a filled orbital of the ligand, which is actually a sigma type of molecular orbital. Now what happens is that you can see here a single hole is present in this case. So the electrons can be transferred from this filled sigma molecular orbitals of the ligand, and in this way the transfer will take place. And because it is an electron transfer, we can equally call it as a charge transfer, right? So as electrons are being transferred from here to here, we will say that charge is being transferred from the sigma molecular orbitals of the ligand to the empty T2G molecular orbitals of the metal-ligand, right? So in the same way, even in this case, vacancies are there. So what can happen is from the filled sigma molecular orbitals of the ligand, once again the electrons, or let us say the charge, it can be transferred to the empty EG molecular orbitals of the metal-ligand, such that now what will happen is that as the T2G set of molecular orbitals are lower in energy, energy is low here, and we know that the energy is actually inversely proportional to wavelength. So what will happen is when these electrons are being transferred from here to these low energy molecular orbitals, they will be showing a band at a very high type of wavelength, which you can see here at 600 nanometers, right? So we can write here that this absorption band is actually arising because of the charge transfer from the ligand sigma molecular orbitals to the metal T2G molecular orbitals, right? And because this transfer is being taken place at a lower energy level, so it will be showing an absorption band at a higher type of wavelength, which you can see here is it is this 600 nanometers, right? And when the electron or the charge will be transferred from these ligands to the empty EG molecular orbitals, what will happen is because the energy here is quite high, so what will happen to the wavelength? It will come down here, and we will say that this absorption spectrum, which is at a lower wavelength, that is 270 nanometer, it is arising because of the charge transfer from the ligand sigma molecular orbitals to the empty metal EG set of molecular orbitals, right? So in this way, we can explain the presence of the charge transfer bands, which once again, let me say here that these are different types of bands in the absorption spectrum as compared to that of the regular bands which arises because of the DD transitions, right? So such kind of bands can also be explained on the basis of the molecular orbital theory, but the crystal field theory can never explain the presence of these charge transfer bands, right? So the last limitation is what? That it does not take into account the partial covalent character of the metal ligand bonds, okay? In order to understand this point, please consider the following nucleophilic substitution reaction, in which you can see here that there is present a square planar complex of platinum, in which there are present 4 chloro ligands here, and at the center what is present is our metal ion, that is the platinum, okay? And now on this side there is present what? A molecule of ammonia, which is the nucleophile, and now this nucleophile will be attacking here on the platinum, sending the chloro out of this system, such that what we will be having is this type of product as the complex, in which the Cl has now been replaced by the ammonia, plus the leaving group, that is the Cl negative, will be present like this here, right? So the important point here to understand is that in such kind of nucleophilic substitution reactions, the attack of ammonia here and then the elimination of the leaving group, this type of reaction can only be explained if we are considering that this bond here, I mean between the platinum and the chlorine, or let us say between the metal and the ligand here, it is having a partial type of covalent nature, right? And if we are not considering the covalent nature here, such kind of reactions can never be explained. And now if we say that we are going according to the crystal field theory, which says that bonding is to be purely ionic, we can never explain such kind of reactions and their mechanisms, right? So the thing is that if we really want to explain the reaction mechanism in such case of nucleophilic substitutions occurring in case of square planar complexes, we have to assume that the bonding in between the metal and the ligand is having some type of partial covalent bond character. And if we are not doing so, we will not be able to explain the mechanism of all these reactions, right? And because the crystal field theory assumes the bonding to be purely ionic or electrostatic, and it does not account for the partial covalent character in case of metal ligand bonds. So using the crystal field theory, we will never be able to explain such kind of mechanism. We will never be able to explain such kind of reactions. So this is all about the limitations of the crystal field theory. Thank you so much.